We weren't done with,
What do you think? We were on a problem like this. So say we've got, we're looking for the intersections of curves. Okay. Yes, sir.
we were on a different problem.
We were, and I've got that. That's our second example. We'll go right back to it. We'll start off with this kind of a warm up, and then we'll do that one.
Are you recording?
I am recorded. Thank you. So find all the points of intersection of the two curves. They're telling us that one intersection occurs when x equals -5. So they're giving us f of x and g of x. What do we remember? Okay, I mean, that would make it easy. You're right. What do you think? Is that a good idea?
But x equals -5 to find the order of pairs.
Well, we could. Yeah, there's one thing we could do. So when we say points of intersection, we're going to want ordered pairs. I'm going to make this easy on you. I'm only going to ask for the x values. We could always plug in the x values and find the y values, right? Because that's what we need. I mean, they're asking for points of intersection. But I want to know just the x values where those intersections occur, let's say. So one of them's at x equals -5. How am I going to find the others?
Very good.
Ideas? Henry, good idea?
I don't think there is
What do you think? Now, how would we, what if we weren't given any intersections? How would we find, algebraically, how would we find points of intersection?
Maybe like, like a game, like with one on the other side, pretty much white, right?
So what do you mean by that?
So put -x squared minus 5x minus 5 to the left.
Of this one over here, equal to that? Exactly, right? That's what we're doing. If we're really just solving a system here, aren't we? We've got y equals x cubed minus 3x squared, blah, 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 and y equals -x squared minus 5x minus 5, right? I mean, these are just fancy function names for y's, right? When we're looking for intersections, we want to find the locations where, for each of those functions, the x and y values are the same, right? We want to find solutions, x's and y values that are going to satisfy both. So this is really nothing more than just solving a system, right? We're just going to substitute. How about if we set, we'll use this as our substitution equation, f of x, really. So that's just y. And that's kind of the key here, is you're just thinking about f of x as being y and g of x as being y, right? So I'm going to solve for, I'm going to make this my substitution equation. I guess we'll put a box around it. And I'll plug it in there, right? And then we end up with the equation x cubed minus 3x squared minus 28x plus 55 equals -x squared minus 5x minus 5. Okay? Now what? Yeah, we got to put it in standard form. Set it equal to 0. So move everything to the left. Okay, if we move everything to the left, I'm going to add an x squared, so I'm going to get x squared. What's that going to give me on the left side? Okay, good. Minus 2x squared. I'm going to add a 5x. Okay, and add a 5. Okay, so there's the function I'm trying to solve. Now, they gave me a 0, though, right? They told me up here above that x equals -5. We're going to keep a list of the zeros. One of them is -5, right? Okay. So what would I do with that? If I know f of -5 equals 0. Divide, what do you mean by divide? Okay. Synthetically, I could divide it out, couldn't I? Right? I could divide my function by x plus 5, synthetically. What's that look like?
5.
So I've got my, what goes out front?
5.
No.
-5.
-5. The 0 is -5. Right?
-5.
So there's my -5. About my synthetic bracket. Okay. Anything else I can do before I even start? No, I'm getting 0 there, right? Okay. So what's that give? Drop down to 1, what goes there? -7, add those. So what, 35?
Well. Oh, that's not good.
And then -60, so it works, right? So then that tells me that one of my zeros is -5, but if I divide that out, what I'm left with is
Another.
x squared minus 7x plus 12, and I want to find the zeros of that. But that's easy, right? That's quadratic. So all I got to do there is, I mean, I can factor that, can't I? So that's going to factor into what?
X plus 4 minus 4.
Okay, and so my other solutions, my other zeros are x equals 4, x equals 3, right? So there are my zeros. And then, so I would need, if I wanted to answer this correctly, if I want to find the points of intersection, I would have to plug all those back into which one? Either one, probably which one would you
The
prefer?
right one.
Yeah, the right one. Pick the quadratic, right, a little easier. Okay, and we can get each of those would become an ordered pair. So let's just do one of them. So for example, the 5 would just become the ordered pair, or the -5. -5, and then I'm going to get, -5 squared is 25 times -1, so I'm going to get a negative 25. Minus 5 times -5 is plus 25 minus 5. So I just get that point. Okay. And, you know, we can see that there's what it would look like if I graphed it. Right, so I've got the red function is graphed in red, blue function is graphed in blue, and sure enough, those are my, 3, 4, and -5 are the x values.
So when
And
we
there's
get-
the one that we found right there, -5, -5.
You get real solutions.
I mean, if there are intersections, yeah. We know there's at least one. If it had only intersected once, then we would have only gotten one real solution, right? Because remember that the real zeros of a function, think about it this way. The intersections would occur when the two functions are equal, right? Do you agree? That's why we set them equal to each other, right? So the real solutions are going to be where the f of x is equal to g of x, right? Now, algebraically, when we move everything to the left side and we create a new equation, well, the solutions are going to stay the same, right? So now the x values that would have, in the top equation up here, would have corresponded to intersections in my new equation that I created. Look, that should be cubed out, that shouldn't it?
Yeah, I was gonna say something about that, but I
So the new equation, this one right here, that we created that set equal to 0, the solutions aren't going to be intersections anymore because they've only got one curve. They're going to be x-intercepts, right? We see that they're going to be zeros. Real zeros are x-intercepts, remember. Complex zeros that have i's in them don't show up as x-intercepts. Right? Just a quick example to demonstrate that. So, like if we do two quadratic functions, what if we do real easy ones? What if f of x equals x squared minus 4? Find the zeros. So if I set that equal to 0, what are my two solutions? X equals plus or minus 2. Okay. Now let's take, what if we do instead g of x equals x squared plus 4? When does that equal 0?
This one is 2i.
Yeah. So if I were to graph those, what do they look like?
One's in the string, one's not.
So we get x-intercepts on that one. This one over here. We don't. Right? So once again, real zeros of a function correspond to the x-intercepts of that function. Imaginary zeros don't. They don't correspond. They're still roots. They still count as to call them zeros, I mean, they are zeros. They're just not x-intercepts, right? They're still values of x that make this function equal to 0, but if they're imaginary, they don't show up on the xy plane, so how could they be x-intercepts, right? Okay? All right, so here's the one we started yesterday, okay? If we're told that radical 11 is a 0, and we want to find all of the complex zeros, well, that's where we can use this with the irrational root theorem, different than the rational root theorem, which we'll talk about later. Irrational root theorem says, and there's some important parts to this, we can't gloss over these, if a polynomial has rational coefficients, then we know that the irrational zeros have to come in conjugate pairs, right? So in other words, if a plus b radical c is one root, then guaranteed a minus b radical c is going to be another. Now that only works if we have rational coefficients. If we had square roots, if we had radicals in our coefficients in the polynomial, then that's not guaranteed, right? But if there are no radicals in the coefficients, then somehow those radicals have to be able to be canceled out, and the way that happens is by multiplying the conjugates together, conjugate pairs. Okay, and think why that would be. Just think totally conceptually here for a second. If I multiply conjugate pairs together, what's the result? Yeah, you see how that's going to work? Now whatever's left over, the terms that are left over are all being squared, and so that would undo any radicals, right? So can you kind of see conceptually, can you kind of make that connection why those really would have to go together if we're not going to get radicals in our polynomial? But they got to somehow go away, and that's how they go away. So this one, how would I do this problem then? If I know that radical 11 is a 0, so let's keep a list of our zeros again. What has to go with it? Negative radical 11. Right? And I could turn both of those zeros into factors. Right? What would the factors be? They go with those. Yeah, look,
Oh, yeah.
what happened there? X minus radical 11 would be one of them, right? And the other one would be x minus negative radical 11, which is x plus radical 11. And those are conjugates. If I take that product, what am I going to get?
X minus 11.
Right? Everybody see that? That's, a minus b times a plus b is a squared minus b squared. Square root of 11 squared is 11. Right? So I know that those two zeros are going to combine to give me that quadratic factor, right? And so then how would I find the rest? Got to divide, right? You see that? I know that this factor times some other one, some other mystery factor, is going to equal that, right? What's the degree of the other factor got to be if I'm going to multiply them together and get x to the fourth? Everybody see that? It's got to be a quadratic factor. So why don't we just call it q of x? We don't know what it is yet, but we know it's quadratic. And combined, those have to equal that. So then to solve for q of x, to figure out what the other factor is so we can find its zeros, because we're just looking for the zeros, I would just divide each side through by x squared minus 11. Right? And then that's going to give me q of x. So can I use synthetic on that? No. I can't use synthetic. I've got to use long division. But it's no big deal. What's my remainder guaranteed to be when I do long division? 0. Okay. And so when I do that division problem, I'm going to get some quadratic factor out of it. And then to find the zeros, either it's going to be nice and I can, well behaved, and I can just factor it. If not, quadratic formula.
Can we go through that long division problem?
Sure. So if we do that long division problem, I've got inside,
Where did the green exit? Just like, oh, okay.
original function. Okay. So my original function divided by the factor I get from those two zeros, when I combine them, I just get that quadratic factor, gives me the factor that's gonna produce the other two zeros, because I should get 4 total, right? Okay. So inside, what do I write inside? X to the 4th? No,
Minus 0.
0x cubed minus 13x squared. 0x, good. Plus 22, good job. Out front, I've got my x squared minus 11. I don't need to have separate columns out front, that doesn't matter, because I'm just gonna put them in the right places when I subtract it, right? So what's my first term gonna be? X to the 4th divided by x squared is x squared. And so if I distribute, I'm gonna get, what am I gonna get if I distribute? I'm gonna get x to the 4th minus x squared. And if I, oh, 11x squared, whoops.
That's a big old eraser.
It is, minus 11x squared. And so if I subtract everything then, those cancel, which they should, nothing there. Negative 13x squared minus negative 11x squared is,
Is
no,
negative 2x.
negative 2x squared, right? Because I'm subtracting a negative, you gotta be careful with that, right? And then I bring the rest of this stuff down. Next term, x squared divides into negative 2x squared, negative 2. And you make a prediction here. What should happen?
Cancel all good.
I should get 0 down there. I have to, right? So let's see if we can make that happen. So when I distribute, whoops. Yeah, when I distribute the 2 all the way through, I'm going to get the negative 2. Negative 2x squared plus 22, and what do you know? Everything cancels. Okay. So then what we're left with, q of x, the other factor, is just x squared minus 2, right? So if I wanted to, and you don't have to do this, but if I wanted to write down the original function in factor form, so where do I have that? Right here. So the original function equals, what was I had x squared minus 11 was the factor I built from the 2 zeros that I knew, right?
Q of x equals.
And then what was q of x, the one that we found?
X squared minus 2.
X squared minus 2, right? And so if I want to find the zeros of all this stuff, well, I already did these. Plus or minus radical 11. I already knew those. What are the zeros going to be from this one?
Minus radical 5.
5 for 2, right? Okay, so there's my 4 zeros. Okay? Good? Okay? All right, so now I want to show you, here's another one. Once again, this is pretty advanced concept, but for you guys, there's a trick I really want to show you. It's called regrouping, right? When you end up with zeros that have multiple terms, this is a really good trick. This is one you want to make sure you get this, because this doesn't always show up in books. Sometimes it does, sometimes it doesn't. But this is one, like when you go to college and you're doing bigger problems like this is a great thing to remember because it makes things so much easier. So if I'm given the 0, 5 minus 4i, okay? And we're going to make the assumption, I didn't put all the instructions in here, but we're going to make the assumption that our polynomials are real number coefficient polynomials, right? Traditional polynomials, as we've defined them in this class. What's another zero that has to be there?
5 plus.
5 plus 4i has to be there, right? We know that zeros always, well, I mean, it is, I don't even know why I even said if this is a normal polynomial, because it doesn't matter. For any polynomial, we know that that zeros, complex zeros, have to come in complex conjugate pairs, right? So, well, I'm not going to belabor that point. You actually could, in complex analysis, you actually could define a polynomial without having a complex conjugate pair, but that's weird. We're not remotely going there. Right? We're talking about regular polynomials with real number coefficients. And so we know that if 5 minus 4i is a 0, let's keep track of them again. Whoops. So if we keep track of our zeros, five minus 4i is a 0, then so is 5 plus 4i. Have to go together, right? Okay, so we know that if we want to factor this thing so we can find the zeros. Well, we need to build a quadratic factor from those two complex zeros, right? So how would we do that? Well, what's the factor that goes with 5 minus 4i? No, the factor that goes with that 0, right? Like in the last problem, we said that if square root of 11 was a 0, then x minus the square root of 11 is the corresponding factor, by the factor theorem, right? So applying that same logic, what's going to be the 0 that goes with, you know what, I'm gonna make these separate. That's gonna be
Minus 5 plus or minus 1.
Yeah, everybody agree? That's going to give us the 0, x minus the quantity 5 minus 4i, right? Everybody agree? Okay, so there's one factor. Okay, what's the factor that's going to go with that one?
X minus
5 plus
5 plus
Okay? Okay, here's my trick, the regrouping trick. If I were to try to multiply this out, can you see that that's going to be a lot of work? I'm going to have to distribute the x all the way through, distribute this complex number all the way through. It's going to be a lot of work to get that thing to simplify. Okay, let's do this though. Let's distribute the negative. So let's ungroup first. We'll distribute the negative all the way through. So there's 2 steps. This is going to be kind of the middle step. If I distribute the negative, I get minus 5 plus 4i. If I distribute the negative here, I get x minus 5 minus 4i. Can I regroup those in a way so they look like a conjugate pair? Because conjugate pairs are very easy to multiply. Remember the trick with conjugate pairs. If I have complex conjugates, a plus bi times a minus bi, what's the answer?
A squared plus
A squared, good, it's going to be a squared minus b squared I squared. I squared is negative 1, so just a squared plus b squared if I multiply complex conjugates together, right? So could I regroup this? Look at that, right? So doesn't that look like a plus bi, where b is 4 and a is that quantity, times a minus bi, where once again a is x minus 5 and b is 4, right? You see that? So if I multiply those out, what's that going to give me then? My complex conjugate, by that property, I know that a plus bi times a minus bi is a squared plus b squared. Well, a is x minus 5, b is 4, right? So that's pretty easy now. We can expand that in our heads, right? It's just a plus b squared. Yeah, x squared minus 10x plus 25 plus 4. So I just get x squared minus 10x plus 29. Oh, plus 16, you're right. Plus 16. I didn't square the 4. So plus 41. Okay, so there's the factor that I get from both of those combined. Right? See that? Okay, so now we can do the same thing we did last time. We've got this polynomial up here, this fourth degree polynomial. We know that this is a quadratic factor of that, guaranteed. So we'll just divide it out using long division, and we know we're going to get some quadratic factor as a consequence of that, and then we can get the zeros easily by the quadratic formula. We don't have to do the whole thing, but let's just write that out. So we know we're getting this. So that's going to equal that times q of x. So we know q of x is just going to equal that divided by that. I just have to find the zeros of q of x. Okay. And the big trick there, why did I give that problem? The big trick is just the regrouping part, right? When you get these, you get these zeros that have multiple terms. When you're subtracting those from x, you just distribute the negative and regroup to make them conjugates, and then the product is easy to do. Okay?
So there's gonna be zeros in that one, and then there's gonna be zeros of q of x.
Right, so we already know the two zeros from this one. Those are those guys, right?
Yeah.
And then to find the zeros of that, well, it's gonna be a quadratic function or quadratic expression, so we set it equal to 0 and we use the quadratic formula, unless it factors or something easy, but probably quadratic formula. Find
Once
the
we
other.
divide it out, and it'll be a remainder of 0.
Has to be a remainder of 0. Right.
Okay.
Okay, so I'm not going to do this one, but can you see it's the same principle, right? We've got a fourth degree polynomial, so we would know
Just gonna
that.
be on the test.
I'm going to give you guys like a challenge problem. It's going to be one like this. Yeah. So would you agree here that
Yes. For credit on the test.
It'll be, yeah, extra value. Yes.
everybody agree there's the factor that goes with that 0? Right. So I'm also then going to have to get x minus the conjugate of that, right? By the irrational root there.
Regroupify.
So all I'm going to do, right, is I'm just going to regroup this. X, I'm going to distribute.
Yes.
I'm going to distribute
And then regroup now.
and then regroup.
Then square.
Right, now I've got conjugates. It's easy, it's an easy product. Okay.
No, man.
All right, so how about these? How much time we got?
13 minutes.
13.
Okay, so we got enough. So these are easier. There's another kind of problem. I just want you to be able to really get this. You got to see this from all angles. So what if I pose a different kind of a question here? Write a polynomial function of least degree. So what's that mean? Okay, so the smallest possible degree. I mean, there's going to be an infinite number of polynomials that would have these two zeros, right? But I want the simplest one. I want the smallest one with the least degree that has integer coefficients, right? So all the coefficients, no fractions, no radicals, the given zeros, and we're gonna make it really simple. It has to have a leading zero of, or leading coefficient of 1, okay? So how could we do that? If I know that those are zeros, how could I build this thing? What do you think?
You can conjugate another one 4 times everything.
Yeah, each of those goes with a conjugate, right? One of them is by the irrational root theorem. We know that if we've got rational coefficients and they're integers, so obviously they're rational if they're integers, then I know that this one has to go with that one has to go with 5 minus radical 5, like the problem we just did. Okay, and that's by irrational root theorem is the blue, right? And then, so this one we know has to go with 2i, and that's just by the complex conjugate theorem, right? Then if I want to build the simplest polynomial, all I'm going to do is just multiply out those factors. That's no big deal. So I'd end up with x minus 5 plus radical 5 times x minus 5 minus radical 5. And then from the red ones, I would just get x plus 2i times x minus 2i, and that's my function, and we'll file that out. Of course, I want to regroup these, right? Okay, that's big. The regrouping thing is big. The old Algebra 2 book that we used talked about regrouping, and the new one we bought doesn't. That's crazy. Let's see how we do it. Okay, so last thing I want to throw at you. Okay, there's another trick. It's a good trick. Allows us to do even a little bit more. So I want to build this up an idea here for you. So what if I gave you the zeros of some polynomial? Okay, I can reverse engineer, just like the problem we just were talking about. I can reverse engineer the polynomial then, right? I can turn the zeros into factors. No big deal, right? So the x equals 5 becomes x minus 5. X minus 6, x equals negative 6 becomes x plus 6 as a factor. And if I just multiply all those out, here's what I get. If I just trust me on that, if I multiply all those out, I'm going to get x cubed minus blah, 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 plus 360. Okay? So here's my problem to you. What if I had started off with the problem, find all the rational zeros of this function, the one that we ended up building? Do you think you could come up with a list of values of x that we could try synthetically, one of which at least would have to work? See what I'm saying? What if we reversed this whole process and I turned this into a problem for you? And I gave you this polynomial. Now this one does not, you can't factor this by grouping. Okay, I don't think you can. I think you can. Could we make this work?
Second.
Oh, I know. I want to, so let's think about this a little bit. Seth's voice is getting tired. We'll do a voice 3. We'll get more tired. So, what do you think? Could you reverse engineer this? Could you come up with a list of possible answers? I mean, how did we get that 360?
Multiply the factor.
We multiplied all of the zeros were all involved in that, weren't they? Because we subtracted the zeros from x, and so when we do this product, you know, when we distribute this whole thing out, I'm going to get a bunch of cross terms, but the x times x times x ended up giving me the x cubed, right? And the 5 times 6 times 12 ended up giving me the 360. I'm not going to worry about the sign, right? You get that? So if we know that this function has to have rational zeros, right? If we know it does, then wouldn't all of those rational zeros have to come from a list of the factors of 360? Everybody get that?
Yeah.
Okay? That's a good trick. That's kind of, we're inching towards what's called the rational root theorem. Okay, what if we did a little bit harder one? What if we did one that had fractional zeros? Okay?
Oh, no.
If we did one that had fractional zeros, no, the same thinking's going to apply. It's really not that much harder. So if I start with the zeros, I could subtract those from x to build the factors, right? Everybody agree? Now, what if I'm trying to build the simplest possible polynomial, one that has integer coefficients? Well, then I could take, now, x minus 5 halves is equal to 0 when x equals 5 halves. That's the relationship there, right?
Yeah.
We've got kind of a two-way arrow. We can always make the connection between this factor and that 0. Well, to make that simpler, though, I've got an equation that's set equal to 0. Why wouldn't I just like maybe multiply each side through by 2 to clear the fractions? If I distributed a 2 through both sides, I'd get 2x minus 5 equals 0. But that still works, right? Because this function, or that equation, still has that 0, right? So we could do that for each one of these. I could multiply both sides through, because this whole thing is really just set equal to 0. I could multiply each side through by 2 to clear that fraction, by 5 to clear that, and by 9 to clear that. And I end up then with simpler looking factors with no fractions in them, right? Now, if I multiply all that out, I get this big ugly polynomial. But the important numbers here are the 90 and the 300. Where did they come from?
Multiplying those three numbers.
Yeah. Right? The 90 came from, it's just the product of 2 times 5 times 9. Right? And where did the 300 come from? Well, the 300 came from the product of 5 times 6 times 10. Right? So once again, if we're starting with, what if we get this new problem that says find all the rational zeros of this polynomial? If there are any rational zeros, wouldn't you agree they have to be built from zeros where the denominators, the factors of the denominators are factors of 90, and the factors of the numerators are factors of 300, right? And so that gives us the rational root theorem, right? That relationship just says all rational zeros that can be written as fractions, must be included in the list of fractions we can build by dividing a factor of the constant by a factor of the leading coefficient. Right? So if there are rational zeros, they have to fall in that list of possible zeros. Have to. Okay? So let's go through a problem like this to see how we can use this. We may not get through the whole thing, but we're going to try. So we've got this polynomial. It says find all the real zeros of the polynomial. So we're going to make the assumption here that it's got some rational zeros. Okay? And there's a good bet that it does, because it's got integer coefficients, right? So what are the possible values that we could try? Well, what's the constant there? Constant is what? Negative 10. Okay, what's the leading coefficient?
2.
So we know then that all of the possible rational zeros have to come from the list of factors, the plus and minus factors. Factors of plus or minus 10 divided by factors of plus or minus 2. And I would just build that list. Okay, so let's think about what are all the factors of 10?
2 and 5.
1, 5, and 2, right? 1, 2, 5, 10 would be the factors of 10, including 1 and 10. Okay, so on the top, we know that we're going to get plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Factors of 2 are pretty simple. Those are just going to be plus or minus 1 and plus or minus 2. So there's a lot of different, the list is pretty big. If I take my denominators to be 1, then we'd end up with the list being plus or minus 1. Now let's write it all out. Not without pluses or minuses. So possible zeros. 1 minus 1. 2 minus 2. 5 minus 5. 10, minus 10. Now we could also divide everything by 2. So we'd get 1/2 minus 1/2. 2 halves and minus 2 halves are already on there, right? I could do 5 halves minus 5 halves, or 10 halves and minus 10 halves, but that's already on there, right? So that's my comprehensive list. If there are rational zeros, they have to be one of those numbers. There's no other possible way it could happen.
One of the green numbers, or one of the green, or.
Or white. Well, now, which ones are you going to try first?
The holes.
You can try the integers, right? And so here's a case where all we got to do, I'm going to show you like a tricky way to use synthetic division here. All we want to do is we just want to addition each of those and see if one of them works. And you can kind of get a sense, like if the numbers are getting bigger and bigger as I'm putting in positives, well then probably you want to go down the other direction, right? But we'll just start with the easiest possible candidates and we'll just work our way through and cancel them off. But here's the good thing. The polynomial is cubic, right? So how many do I need before this becomes really easy? How many zeros do I have to find? Just one. If I find one and I divide that through, I'm going to end up with a quadratic factor left over, and then I can get those two with the quadratic formula. So once I get it to quadratic, I'm essentially done, right? I just got to find one that works. And so we would just try that by, literally just going through and additioning these to see which one works. Okay, I'll show you a little trick tomorrow for doing that, then you can work.
I'll show you.